I didn't also ask you. Okay, you can go ahead.
Okay, yeah, thank you. Thank you very much, Hossein, for the invitation to speak there, and thank you all for coming. So I'm going to talk on rationality of mums in two functions, and somehow there is a pun in the title, which I don't know is due to Vadim Zutidin or something like this, but I will try to. Okay, so this talk. I'm not exactly sure about what the audience is and so on. And I took a peek a couple of weeks ago to see what is going on. In the end, I think the talk is going to be there are kind of two parts to the talk. Okay, the first part, as you will see, is going to be very elementary, in fact, and then sort of I hope there is some message in this first part. And then the second part is sort of trying to motivate why this first part is interesting in the first place. Okay, although I think certainly Hossein will immediately appreciate why this first part is interesting, and then but then maybe not so. Okay, you might have some objections to the second part. Anyway, let's get started. So so the second part is going to have a lot of assumptions, and if I'm making too many assumptions in the beginning, then just let me know as well. Okay, so somehow the motivation for this work is goes back to, let's say, classical or mirror symmetry, and by this I still am very excited about the classical version of mirror symmetry, which most of you have heard. I assume that there is this correspondence between enumerative geometry of most generally symplectic manifolds and some variation of Hodge structure of complex manifolds, which is the B model. And you will also have heard that underlying this there is a physical duality. Okay, so this comes from physics, and this means that it means that there is a complete equivalence of physical theories, and means that if you have something on one side, you kind of have to have it on the other side. Okay. And in mathematical terms, there's equivalence of categories known as homological mirror symmetry, which also says whatever you have on one side, you have to also have on the other side. Okay, so if there's some things you have on one side and you can't find it on the other side, and in some sense you're in trouble. Okay, so the thing that gets me still makes me continue try to understand what's going on is this complete equivalence, and the observation which I didn't know about when I first entered mirror symmetry, but which at some point crops up, okay, which is the arithmetic of algebraic varieties, and that it enters in some ways, and in fact in different ways, into the B model, right? So when you talk about variation of Hodge structure, at some point you have to ask about arithmetic properties, and this is in the title of the seminar, Arithmetic of Periods. And so in some sense, the first question, I mean, this is a big question, okay, so what is actually the interpretation of this arithmetic properties of periods in the A model, and in some sense also in physics? Okay, so there are some number theories going on in these periods, and you want to know, does this have any interpretation in the A model and in physics? And then you can, because this is kind of course, dualities always work both ways in physics. You want to ask also the other way, and that's $1 million question probably. Does mirror symmetry or physical dualities, do they have any bearing on, say, arithmetic geometry? And that is, much bigger question even. And I'm not even the first one. I'm not claiming to have any answers to this, but I want to sort of explain some aspects of the type of questions you can ask in there, and why you want to ask these particular questions. I mean, what is special about them? So, okay, so what is sort of the status that we have? So, classical mirror symmetry takes place at these points of maximal unipotent monodromy, MAM points, in a moduli space of Calabi-Yaus, and I will always have in mind Calabi-Yau threefolds, and I will mostly have in mind the quintic threefold. Okay, and in the second part, or even at the beginning when I motivate things, I will kind of assume that you're familiar with this quintic story. And I mean, I know some people are familiar with this very much. So It's not a completely unjustified assumption. And what one of the points is going to be, sort of in the second part, is that, I talked about this enumerative geometry and this enumerative interpretation of these periods. And something that was there in the beginning of mirror symmetry, it's mentioned in the first paper of Morrison, but then it's not mentioned basically at all anymore, is that the interpretation in terms of enumerative geometry depends on some feature which is a rational structure at the MUM point. And just to immediately say what I mean by this, I mean just that if you take the periods and you expand them in the canonical coordinate, you get rational coefficients, okay? At some point, that's all I mean. There is no mathematical reason that I know of why these should be rational numbers, okay? When you expand the period, when you expand this prepotential. And I want to, just naively call this a rational structure that appears at these MUM points. And if you don't have it, then this enumerative interpretation is put into question. And the point is that, there is in fact no reason, and sometimes there aren't. These coefficients are not rational numbers. And so by the message I said at the beginning that whatever you have on one side, you have to have on the other, it sort of begs the question, or forces you to ask the question, what does this mean in the A model? Okay, and I still don't know, even though I've been thinking about this for many years now. But what I can sort of report, there are sort of two things that are new in the last year or two. The first one is some work by my student Felipe MÁ×ller that has a bearing on this, and I will try to explain what the relationship is. And that's the statement that rational two functions are abelian. Okay, so here rational has a slightly different meaning has a different meaning than the rationality of this MUM point, but we'll explain what this statement is. And that's, the relationship to mirror symmetry will not be clear, but it's an elementary kind of statement, and I hope there will be some, it will, the second sort of thing is these examples actually of not quite geometric MUM points, but differential equations which have these irrational MUM points. And we've been studying those. I've known about those for a long time, but we've now started actually look at them more closely with Albrecht Klemm, Ducrot van Straten, and a student of Albrecht's. Okay, so I hope this is all right for the motivation. So here's the plan. So as I said, I'm going to go slightly, I'm not going to go in the way that I just sketched in terms of motivation, but I'm going to start with an elementary thing, which are these two functions and what it means when they're rational and abelian and so on. And then I will sort of embark on the second part, which is the more technical thing about Calabi-Yau and Hodge theory, and then I will give these examples. So in some sense, I should, I've been giving this talk before, well, okay, you let me know, you interrupt me, okay, when things are not clear, when you're missing the motivation for these two functions, then we can jump to the second part. If you want to see the examples, Hossein Hossein knows the audience and he understands what I'm talking about. So if you feel that there are things I should say from the examples in order to make people appreciate what I'm telling about two functions, then tell me what I should say, okay? Is that a good plan, Hossein?
Yeah, okay.
Okay.
Let's go.
So here's two functions. So what do we have? So in fact, 2 can be also S, okay? So it's just a mirror version of S. So S can be any natural number. And then we have this definition of an S function. And here we have with rational coefficients. And what we mean by this is, can you see the pointer actually?
Yeah, we see.
Yeah, okay, you can see the pointer very well. So at least I have something to point. So you have an independent variable z, and you have a formal power series with rational coefficients and no constant term, which is called W. And just by formal power series, you can rewrite it in terms of polylogarithms of order S, okay, which is this familiar power series. Of course, this converges, but the formal power series you can rewrite in terms of these polylogarithms with, you have this z to the d here, and these coefficients nd, and you call this thing an S function. if these coefficients are integer numbers. Okay, so that's the definition. That's the notion of an S function. Okay, and if you have studied mirror symmetry a little bit, you will know immediately where these things come up. In fact, they come up in for S equal to 3. When you look at these mum points for mirror symmetry and you expand the prepotential in flat coordinates. Okay, so as I said, if you know mirror symmetry and you have seen this, and well, otherwise, it's. I mean, I will explain the second part how this comes about in geometry and Hodge theory. But otherwise, you can just take this, or let me say why this is important in mirror symmetry related to what I said at the beginning. Okay, so you have this function which is the prepotential, and that's some combination of periods for these degenerating Calabi-Yaus, and there is some thing here which also is interesting from the arithmetic point of view, is particularly the zeta of 3 thing. But then there's this power series, and you have to choose a particular local coordinate and this degeneration. And if you expand this, then in all examples that people have studied, I would say, you have a power series with rational coefficients, okay? And it turns out that this is always a 3 function, okay? Which means that if you re-expand in terms of these trilogarithms, then you get integer coefficients. And that's important, because under mirror symmetry, these coefficients have an enumerative interpretation. And okay, so there are sort of 2 flavors. There are the Gromov-Witten invariants, which are rational numbers, because you count maps, and there are some singularities in the space of maps, and that leads to some denominators. But then there are more physical invariants, but now quite well understood mathematically as well. These are called BPS invariants, and these count objects in the category, or I mean, at this level, you just say they count curves instead of maps, and these should actually be integers. Okay, they're actually supposed to count. They're supposed to be integers. I mean, if you want, there are some dimensions of Betti numbers or dimensions of cohomologies of some moduli space or something, and if these are smooth, then these should be just integer numbers. Okay, so these BPS. So, but for this, as I said, as I mentioned, it's very important to begin with, even that these are rational coefficients. And what's going to what is true is that this rationality assumption is not always satisfied. Okay, but let's for the moment go back to these 2 functions, and let me give you a little bit of. So what you in some sense, to understand what I'm going to say, you have to appreciate this expansion. So you take this power series and you expand it in these trilogarithms, and you define the enumerative invariance by expanding relative to this trilogarithm. And the question when you have irrational coefficients is, what is the analog of this? How do you define integer invariance in this case? And so that's sort of what this story about the 2 functions are going to come down to. So there are some elementary things you can do with these formal power series. Okay, so you have this logarithmic derivative, and if you have an S function, then the derivative is an S-1 function. The opposite, of course, is not true. So you can integrate formally, okay? And then if you have an S-1 function, then an integral of it is not necessarily an S function. But what is, you have these shift functors, these shift operations where you raised it to some power L, and that's also then an S function. You can convince yourself, I mean, that's sort of built into the definition, that any S function can just be written as a formal linear combination of shifts of the polylogarithm, right? So I want to say this in the sense, and you can make this a little bit more precise with this right topology, that the space of S functions is actually a rank 1 module over this. So, I mean, it's just generated by this one function, which is the polylogarithm. So I call this a basis, okay? Yeah, and there's one thing, of course, the simplest one is the logarithm. That's just to record this. So there is this notion of rational or algebraic S functions, and that's, as you might expect, if this function is rational, okay? But what comes from something rational in a simple way, and one way to say this is, so for example, you take this logarithm, right? So you take the exponential of li1, that's going to give you a rational function. And if you have an s function, you take s minus 1 derivative, so to get to li1, and then you take the exponential. And if that's a rational function, then the s function is called rational, and algebraic and so on. And or you can have locally analytic thing. But for the moment, what I want to focus in is this rationality of the s functions. Okay, so okay, so let me now digress and or digress a little bit further and in order to motivate these irrational coefficients. So if you think about this statement, the definition of s functions for a little bit, you will realize that that has to do with congruences between these coefficients. So, I mean, you have these rational numbers, and then the question is, what are the congruences between these the numerators? And I mean, you can see, you can formulate this in terms of these congruences at all primes. And a simple way of writing it in terms of the Frobenius operator. So you take the Frobenius unformal power series, which just raises z to the pth power, and then you can say that you have an s function if and only if this Frobenius on power series divided by p to the s gives you something which is only p-adic integers as coefficients. Okay, so I hope this is, morally clear, that you can have something like this. I want to, well, there is, again, I'm not exactly sure about the audience, but this might remind some people about this so-called work integrality lemma, okay, which is a statement about of exponentials of these power series, and that sort of is the case of s equal to 1, and also has this Frobenius statement built in, and that work integrality lemma, in fact, is studied also when you have irrational coefficients. And let me skip this framing. Actually, I think this is, unless you want to know about the framing. So I can maybe go back later why these two functions are special, but let me actually go to two functions with algebraic coefficients. Okay, so once you have written it in terms of the Frobenius, then you can have this idea of generalizing it to irrational coefficients, in fact, to take a number field and to let this Frobenius also act on the coefficients. And here is, it's a slightly non-standard way of writing the Frobenius. If you are teaching number theory, then I'm sure you're not doing it like this. You actually have these Frobenius at all these primes above the rational prime, okay? So we're always looking at the number field as an extension of the rationals. So I have trouble defining S functions for intermediate extensions, but what if you're doing this relative to the rationals, then you take rational primes and you have the Frobenius, which for a physicist just means you are finding approximations, successive. So from us, theorem tells you that x to the p, if you have x, a solution of a polynomial, then x to the p is a solution mod p, and all you're doing is you're improving this mod p squared and so on by using Newton's formula, okay? And you can do this, if this is not a ramified prime, then you can do this at infinitum, and that's the definition, that's my definition of this Frobenius at p, okay? And so if you have a formal power series with coefficients in this number field, you can look at the same thing at p, where you just sort of take this p-adic completion for the coefficients, and then you have this definition of an S function with coefficients in this number field. And let's see. So
Johannes, is it possible also to define directly? I mean, like rational numbers, just writing log s and.
That's exactly the question. Yes, no, that's the question, right? So indeed, so let me go back. So I defined S functions with rational coefficients by this formal power series, and by the fact that the integral when you expand them in polylogarithms, and that's motivated by this problem that the way that this mirror symmetry was first stated is that you expand it in terms of the trilogarithm, you get integers. Then I reformulated this a little bit more abstractly, and I said that in some sense this trilogarithm is only a basis, okay, and you can have different bases, okay. So for example, you can take li3 plus li3 of z squared, okay, so that's also a basis. And you can define coefficients with respect to this other basis. It turns out that the ones which are canonical are the ones which are defined relative to this polylogarithm basis. And now if you have so later we're going to see that sometimes you actually have the geometry in the B model, this period business gives you coefficients which are not rational but take values in a number field. And what you will see, or what the theorem says, is that in fact you still have a 3 function with algebraic coefficients. And what you want to know is how do you extract integers from this? Okay, how do you even so there's some integrality, but you want to know how do you extract integers, and that's why you ask the question, what is a basis, right? So does that way of phrasing the question make sense based on what you asked? What you asked is basically what is the basis in which to expand and then recover integers, and that is the question that I want to ask. So I have some examples for this, but an important example is, and so that's where this abelianness comes in. So if you have a root of unity or a cyclotomic field, then it's very easy to write down an S function, because you just stick in this, then the Frobenius is just literally raising the the root of unity to the pth power, and you just stick it into the polylogarithm, and then you get immediately an S function. And if you have a cyclotomic field, you talk all relevant roots of unity, and that gives you a basis, okay, for these S functions with coefficients in this cyclotomic field. And then by Kronecker-Weber theorem, if you have an abelian extension of Q, then you will always get a nice basis. You will always get a basis, and it's sort of canonically related to these to the polylogarithms. The question you don't know the answer to is, what is a natural basis if you have a non-abelian extension? And that's sort of the question that you want to ask if you want to ask when you can give an enumerative interpretation to these periods. So that is the question about the basis, and so okay. So then, what did my student do? Okay, so we so what we asked. So you can ask. So how do you characterize a nice basis? Okay, so in the rational case, for example, you can say, okay, the natural basis are these polylogarithms. And well, what is their property? I mean, they're sort of simple, right? I mean, the coefficients are just 1, but what else is there? And one way to say it is that at least they're rational, in the sense that if you take s-1 derivatives and the exponential, you get the rational function. So you could ask the question, do we at least have a rational basis of S functions when and then want to look based on this, right? So for example, how do you so look at this example here, for example. So this is this is a number field with Galois group Z mod 3, and there is a simple polynomial, and if you take the log of it, then and then you integrate, then you get an S function. Okay, so that's a simple exercise to check that, you know, all these things that are just the Frobenius elements for these number fields. Okay, so what my student showed, in fact, is that that's not you can't have that. Okay, so if you have a rational 2 function with algebraic coefficients, then these coefficients have to lie in a cyclotomic field. Okay, and in fact, the intuition behind this is actually quite simple. Okay, so if you have right, so look at this polynomial, right? So if you have what this, you know, you expand it and you expand the logarithm of it and so on, and then what is written here. So x is some algebraic number, and what's here are the Frobenius images under the corresponding Frobenius for these primes. So, you know, that's Frobenius at 2 on x, and that's Frobenius at 3, and so on. And you can express this in a simple way and a simple regularity. And if you could do this, I mean, here it's the Frobenius on the nose. Okay, so for a 2 function, you don't want the Frobenius on the nose. You want it only mod p to some power, for example, p squared. Okay, and that's a slightly that's much less than knowing the Frobenius p-adically. And what you but still, if there were a polynomial, so that when you expand it, you get the Frobenius mod p squared, that would be imply some, you know, kind of regularity among these Frobenius elements, which we don't know about in the non-abelian case. So, I mean, I don't know much about number theory, but what I know is that if there is regularity among the Frobenius, in the sense, for example, that you can express it in terms of some congruences for the primes, then you have an abelian extension. And one of the questions is to understand this Frobenius for non-abelian extensions for all these primes. So, but still, it was not so. It was not. There was the intuition, but it was not completely obvious because you're only requiring the Frobenius mod p squared, not the complete information. Okay, so that's this first theorem. Okay, so it tells you that I mean, it's a little bit a negative result in the sense for asking the question, but it tells you have to go beyond rational functions to find a nice basis of 2 functions or S functions a fortiori in the non-abelian case. So that's sort of the first part of the talk. This one theorem. There are other results on 2 functions related to this framing, but maybe I should pause here and see if there are questions and that I'm making sense at all, and at least striking some chords with somebody.
Well, I think the main objective was 3 functions, but what was the reason to focus on 2 functions? I think I missed this one.
Okay. Well, 2 function is the first non-trivial one. I mean, well. Okay. So in the classical literature, people only talk about 1 functions. Okay, so Dwork only talks about 1 functions, for example. Okay. I don't know. I mean, I'm not doing justice to Dwork probably, but this Dwork integrality lemma is very simple from this point of view of S functions. I mean, it's like many lemmas which are important. It's very simple, but it's the first non-trivial one. So, you know, for example, this intuition about the Frobenius, you could expect it to be to still somehow work for S equal to 2. But the theorem tells you as soon as you want more than gen x to the p, maybe I should have said this, right? So for S equal to 1, you immediately get the rational basis of 1 function, because you just take 1 minus xz, and then, you know, x to the p's power always is the Frobenius mod p, right? It's when you want more mod p squared, then you get into trouble if you don't have regularity among the Frobenius elements. And so there are more things that are special about S equal to 2. Sorry, for example, this framing business. Okay, so there are some things related to inversion of formal power series, which is very special for S equal to 2. And you don't have for S equal. And then in geometry, so that's going to be now in the geometry. 2 functions arise when you extend, your Calabi-Yau threefolds by algebraic cycles. So then you have these 2 functions appearing. Other questions? Okay. Okay, so I don't know. I might again. That's the next couple of slides. I mean, I tried to condense in a very few number of slides somehow this entire discussion of these mum points and how you extract the periods. It's not all that crucial. It's sort of a talk on its own to explain all of this. So you might not have seen this, and I mean it's written in a sort of more abstract way than physicists usually talk about this, just because that makes it makes the transition or the connection to how you prove that these things are three functions simpler. Okay, otherwise you don't have it. Okay, so what we're talking about are some families of Calabi-Yaus. Okay, I cannot push me. Can I highlight things? I sort of like this, right? I don't know if I have a. Does anybody know by heart how I get a pointer in I remember.
No, just the mouse. I think you can. I don't know.
I think Keynote has it, but only if you're on the iPad. I think that's the problem, right?
But if you just highlight it with this blue thing, just the paste copy it to the query also.
Okay, that's okay. That's good enough. So just to focus your attention a little bit. So think of the quintic. Okay, think of the quintic threefold family. Okay, so that's what I have in mind anyway. So you have a family of Calabi-Yau threefolds, and the fibers have Betty number. Sorry, this should be B3, obviously. Third Betty number equal to 4, and there is this degeneration, which is this has this maximal unipotent monodromy. Okay, and to this variation, this assumption is made down here, and so to this variation you have attached this variation of Hodge structure, and when you go into this limit, then you have this monodromy weight filtration, and you get this variation of mixed Hodge structure, and the sort of what I guess Deligne or Morrison and Deligne explained is that in fact the point of the mirror symmetry calculations, and that's sort of this Hodge theoretic statement, I think, is that of course there are many other ways. Hossein, I should have sorry, there are many other ways of thinking about this as well. Okay, but I'm just thinking in the original mirror symmetry way, and then as explained by Deligne, that the point is you have these this mixed Hodge structure, which is built up of these Tate factors. Okay, so that this thing has this composition series where each one is this Tate Hodge Tate structure. Okay, and then the extensions here are just simple functions, which are exactly the periods you calculate that you solve from the differential equation. So you have functions which characterize this, how this Hodge structure is built up at this mum point, and they're sort of, first it looks like maybe there are some three functions because you have this composition series has these three steps. It turns out that because of the duality, this and that are the same, and are basically what's called the canonical coordinate. Okay, and so that's this Q. Okay, so this is the first step in this extension, and then there is another one, which is the one in the middle, if you want, and that encodes the Yukawa coupling or the prepotential, and so on. So the point of this discussion is just to bring home the point that when you are in this situation, you don't need to. Of course, in the end, if you calculate, and as physicists you want to calculate, you solve differential equations. But if you just look at the geometry, it's completely intrinsic. Okay, so right, so I did not need to introduce coordinates, for example, to begin with. Right, the canonical coordinate was one of these extension classes here in this construction of the mixed Hodge structure. So so that's the mirror symmetry. Now I can or this the calculations are on the mum point that then have this mirror interpretation. Is that okay at this level? Or do we need to say more about this?
No, I think it's okay. I mean, well, at least in the classical period language, I think many of my students, they have seen already.
Okay.
But not this language.
So yeah, I mean, I'm not necessarily, as you know, would not necessarily. I mean, I had to learn this language because I wanted to understand how you, sort of understand the fact that they're rational numbers, that the coefficients then have this integrality property, and for this you need to switch to the p-adics, and that was you just couldn't do it just using complex geometry, right? So so this is so right. So that's how you prove it, right? So in examples, okay, what happens is that these families of Calabi-Yaus, they're actually I mean, when you talk about the rational Hodge structure, you want to be over the complex numbers, but they always arise as complexifications of families which are actually defined over Q. And for example, the quintic, which you will have seen just as rational coefficients, and all the constructions that people give using toric geometry and what have you are sort of defined, arise as complexifications of families defined over Q, right? So you write equations which have just rational coefficients. And if you do this, I mean, you sort of, people then assume that not only the family is defined over Q, but there is a sort of somewhat more subtle point, which I have, I probably have trouble nailing down completely correctly, but it's the statement that actually the MAM point is rational. Okay, so I've kind of already said what I mean by this. I mean, it means that the coefficients, when you expand the prepotential at the end of the day in the canonical coordinate, actually has rational coefficients. That's sort of the most elementary way of saying what you mean by rational MAM point. But you can, make a somewhat, you can make a somewhat stronger statement, okay, which somehow means that it's a rational space of the family and so on, and that the localization at this MAM point is also defined over Q or over this formal disk over Q. Okay, so that's sort of the rationality. And once you have rationality, then you can understand why this prepotential has this three-function property. Okay, so this is sort of this theorem of Kontsevich, Schwarz, and Vologodsky, which explains that you have that this Yukawa coupling, which is one of these extension classes in this Hodge, in this mixed Hodge structure, actually is a three-function. And the way this goes is that this Picard-Fuchs equation that you use to do solutions at the periods, right? Usually you think of them in complex numbers, but in fact that only depends on this thing being defined over Q. Okay, you don't even need any you don't need this complex topology to study the Picard-Fuchs equation. Okay, that's the interesting statement. If you want to sort of nail down the canonical coordinate completely and the prepotential completely, then you need to you want to define it intrinsically, right? Then you have this in the Hodge theory. You have this lattice, okay, which I mean somewhere here, right? The lattice, and that lattice depends on the complex topology. And what Schwarz and Kontsevich, Schwarz, Vologodsky point out is that if you, instead of taking the complex topology, you take the p-adic topology and you do some gymnastics in p-adic Hodge theory, then well, the functions are the same up to maybe some small subtleties involving integration constants. That's in fact where everything is, but in the p-adic world, it's very easy to see that you have a three function, okay? And then what you have to show is that the p-adic function and the complex function, that they sort of agree, And they agree because, in fact, the solutions of the Picard-Fuchs equation up to these integration constants. So the message at the end of the day is, if you, let's see, I'm kind of done, yeah, with this part. Okay, so the message at the end of the day, again, is that if you assume rationality of your family and of the MAM point, then by this theorem, you actually have this three-function property, okay? Maybe up to some subtleties involving. Okay, let me just say this is the theorem. And
may I ask one question?
Yeah, sure.
So if so here, why is it 3? For 2 or 4 or other numbers, this is not true?
Well, 3, we are in the yeah, we're talking about Calabi-Yau threefolds, right? So I probably said this up
only
there.
for 3.
I mean, it's this. So this definition of the canonical coordinates and so on. This business here, for example, that very much depends on the number 3. Okay. I mean, you have mirror symmetry or you can do somewhat similar things also in high dimensions, but it's not quite as constrained as in the case 3. Are you asking why this? Okay, maybe. So the one thing I know, or maybe I don't know anything, but the one thing that I'm told, or that enters into this proof, is that the Frobenius in this world of p-adic Hodge theory on the S step in the Hodge filtration is divisible by p to the s. That's where this comes from. Okay. So the point is, if you have dz, okay, very simple, and you take z to the power p, then it's p times dz. Okay. Right. And so if you have, let's say, and dz is the sort of holomorphic guy. So if you have, let's say, 3 dz's, dz1, dz2, dz3, you take each to the p's power, you get 3 to, you get p to the 3. So it's divisible by 2 to the 3 if you have the S step in the Hodge filtration, and that's why this 3 comes from.
Okay.
Does that help a little bit?
Yeah, thanks.
Okay. Okay, so right. So now let's connect this back to what I said in the beginning. Why this rationality and this integrality is important for this interpretation. I mean, I kind of already said it, but saying it again here. So you need the rationality in order to interpret them as Gromov-Witten invariants in the ordinary sense. Okay, so in the A model, in Gromov-Witten theory, people define Gromov-Witten invariants of symplectic manifolds. And these just are rational numbers by definition. There is no way around it. Okay. So, if you believe in mirror symmetry, and in some sense that let's say, so mirror symmetry would say at least that, well, I think, okay, let me slow down a little bit. If you had if these coefficients were not rational, that the coefficients of this prepotential were not rational, you would not believe that there is a Gromov-Witten interpretation in any A model. Okay. But the point is, and that's why I mentioned this equivalence of categories, is that if you have a degeneration of Calabi-Yaus, you also have additional things. You have, for example, the physical interpretation, or you have this homological mirror symmetry, and these additional structures suggest, or very strongly, convince you that there should be an A model. Okay, because you can kind of reconstruct, from a categorical point of view, you can reconstruct an A model, from the category. So so if you find examples where they're non-rational, then very much this puts this entire picture in question, and that's why I think this is just very interesting. And so this is the rationality. And then, as I said, it's essential. The integrality is a little bit, well, sort of comes second, but it's also very crucial for then having an interpretation in, well, in physics language, a BPS interpretation, or an actual enumerative interpretation. Yeah, so there is, if you have studied these differential equations, then you will know that, you know, these integration constants I was talking about, you fix them by well, one way to fix them is by global monodromy of these differential equations. Okay, so now we come to the examples. Okay, so that's where, so the point of the examples is that there in fact exist examples where you have non-rational coefficients, and that's why I want to get at. Okay, so this is the quintic example, and I understand then many of you will have seen this. Okay, so this is the Picard-Fuchs differential equation satisfied by the period of the quintic, and the prepotential takes this form, and then down here you see this. Do all your students do this calculation, Hossein? Or they immediately modulo form?
No, exactly this calculation I have always mentioned.
Okay.
I mean, this calculation 2875 and so on. I think at least 3 or 5 they know.
Okay. So, but right, so you have this this thing here, which is this, you know, if you get 609,250 if you subtract this minus this divided by 8, then you get 609,250, and there's a q squared missing here. Apologize. Okay, so as I said, there is a lot of you know, many other examples of this, and in fact there is this catalog, this Almquist-Zudilin catalog of Calabi-Yau differential equation, which are just fourth order operators which have these MAM points, and this all the other properties that you want from Calabi-Yau in order to interpret as a Calabi-Yau differential equation. It's coming from Calabi-Yau. I mean, it's not entirely well. At least the initial definition now, this is understood a little bit better how much of this is redundant, how many of these conditions are redundant, but that's not all that important for me. Okay, one of the points is that they actually require when they write down these equations that this MAM point is defined over Q. Okay, so they don't in their constructions they don't have they don't allow for MAM points which are not defined over Q. But one of if one doesn't want to do extra work, then one can look for other MAM points in them. Okay, so that was the first thing that we did, because sometimes these operators that they write down, okay, have other MAM points. I mean, they have other singularity, and sometimes these other singularities are also of MAM type. And you can ask, so are these defined over Q? I mean, it turned out that all the operators that are actually on the list only have rational MAMs. Okay, so then you can think all MAMs are rational. But as you know, that's not a true statement that all MAMs are rational. So there is, in fact, an example, and that's an example that was on the list, and it didn't really know what to do with it. So it's not the first one we studied, but that kind of brings home this point. Okay. So if you look at this operator, it satisfies all these conditions that you want of a Calabi-Yau differential equation, but not the integrality of the prepotential. So instead, in fact, it has, and maybe one should, one should probably look at this in a little bit more, maybe should have something to write or so, but so this is the prepotential, exactly the same as for the quintic that you write down for this differential operator, which is up here. And what you see, no, that's not what you, so if you write it down, then you don't have the square roots of 2, okay? So remove the square root of 2, but what you see, and that's sort of, you can experiment that if you twist this trilogarithm with a quadratic character of 2, which has this periodicity 8. So it's 1, and if p is 1 or 7 mod 8, and it's -1 if you have 3 or 5 mod 8 or something like this. And if you twist it, then you again recover integrality. And the so that means that, you know, this thing is not a 3 function with rational coefficients, but in fact it's a 3 function with coefficients in Q extended by square root of 2, this real quadratic number field. And in fact, if you if you actually go through the calculation, you see that that's actually what's predicted by mere symmetry, because if you just take right, so usually the relation between Q and Z, the canonical coordinate and the independent coordinate in this differential equation is that Q is equal to Z plus higher order terms, right? So then the coefficient here is usually a 1. But it turns out that this 1 is actually an integration constant. I mean, the Hodge theory really tells you have to pick the correct integral generator. And that's, from the differential equation point of view, is an integration constant, which just happens to be 1 in most cases. But this is an example where it's not 1, it's square root of 2. So if you do the calculation correctly, this Hodge theoretic calculation, and you indeed find that the canonical coordinate has the square root of 2, and then your prepotential has square roots of 2 in them, and then, you know, it's a 3 function with coefficients in this abelian number field. Okay, that's sort of the first example. And then there are more examples. The thing about this example is that the irrational number is actually not visible in the operator, which is a little bit special. So you can then find other operators which have, you know, the irrationality in the differential equation built in. So that's I think that's actually the first operator that we sort of studied, that is in the algorithm of Almqvist, Zudilin, and van Straten. Okay, so it's one of the constructions that they make, and they take Hadamard products of families of elliptic curves, and then you can get these kinds of differential operators. And if you do the same calculations here, so again, you do it precisely. Now you know about this integration constant, and you do it precisely, and then you find that, I mean, of course, the tail of this expansion, in fact, is a 3 function with coefficients now in this number field. So I don't know how much interest there in these other coefficients here. I mean, if you just, I can just make a slight comment about those. So in the ordinary case, you have zeta of 3. In this case, you also only have zeta of 3. There's no other term. But in this case here, where you have the square root of 5 in the differential operator, you also get this special value of an L function at s equal to 3. And this is I mean, it's a Dirichlet L function where you have this Dirichlet character here. Okay. Just as, so it all fits into this thing. And what I yeah, so you have this 3 function. So what is the I mean, can we prove that it's a 3 function? No, that's something you can ask. So this theorem of Schwarz-Vologodsky, in fact, keeps working if you don't assume that you start with a family defined over Q. Okay, so it also works for a family defined over a number field. You still get this integrality statement in the Frobenius, in the sense of this Frobenius. So the theorem says that the tail of this prepotential is a 3 function with coefficients in the number field over which this degeneration is defined. So that's what this theorem says. What you don't know in general is how to expand it. Okay, so you don't know in general how to rewrite in terms of the trilogarithm. That's what I said. And because we don't know the basis, but the integrality is there. And also, we don't have any example, which is not abelian. Okay, so all examples of operators with irrational mums that we are able to construct have coefficients in abelian number fields. In fact, always real quadratic. But something which is nice about this operator, that in fact it's not too far away from geometry, because, you know, as I said, you can have there are these Hadamard products, and this Hadamard product, I mean, that might not be, you know, too familiar, but you have these families of elliptic curves and some kind of convolution product that you can make over these families of elliptic curves. So, and then you get a family of threefolds, and that's sort of a geometric operation, and you can try to do this on some other mirror side. So there is hope that if you do this correctly, you can understand why, from the A model point of view, actually these things are irrational, and but maybe still have this integrality. Okay, so that's this example, and now the last part is about these two functions. Okay, so this is this extension. So it's kind of all I know about these irrational mumps at this point. But the other thing is that these extensions, so this is the s equal to 2 case. I could also skip this, unless you want to know why s equal to 2 is also interesting from the Calabi-Yau point of view. So this has to do with these cycles.
Oh.
Should I go over it? I mean, it's not.
You have 4 minutes.
That's not, in some sense, that's not new stuff. That's older stuff.
Okay.
But so the thing is, you add to your family of Calabi-Yaus, you add a family of algebraic cycles. Okay, so in each Calabi-Yau you have an algebraic cycle, and then that gives you an extension of Hodge structures by this algebraic cycle. I mean, somehow in terms of period, these are instead of talking about closed cycles, you have cycles which end on this algebraic cycle. So think of a Calabi-Yau threefold. You have a curve, which is a complex dimension 1 object inside, and then you can have a 3 chain which ends on this thing, and you integrate the 3 form over this 3 chain. And if you include these periods into the story, then you get this this extension of the story. So formally, you have this extension of Hodge structure. At the level of the differential equation, you have these inhomogeneous Picard-Fuchs equations. Okay, so that's the type of differential you have. So this is, for example, this is the quintic operator, the quintic differential operator, and it operates on this, semi-period or open period, and you get some function, and that's the inhomogeneous Picard-Fuchs equation. And what this theorem of Schwarz-Vologodsky says, if you apply it in this situation, is that this period, this extending period, where this function which describes this extension, in this case, this one additional extension, is a 2 function. Okay, so that's why when you talk about algebraic cycles, you have 2 functions that enter even in the Calabi-Yau threefold. So so that sort of was the first point where these irrational coefficients were discovered, and or were noticed. Sorry, I shouldn't. It's not discovery in the physical sense, but was noted or pointed out that you have these irrational coefficients, because for algebraic cycles, in fact, it's much easier to write down examples where which are not defined over Q. So these are examples of cycles on the quintic where the coefficients are not defined over, are not rational. And you get, then you have these types of number fields, and these are non-abelian number fields. So that sort of, was the motivation for asking this question about 2 functions and bases for 2 functions for non-abelian extensions, which was kind of answered in the negative, but I still think it's very interesting. And this is the inhomogeneous Picard-Fuchs in this case. It's a complicated beast, but, how to say? I mean, from the point of view of, okay, let me make this, I will stop after this, okay? So this is the last statement that I will make, but it goes back to this intuition that I mentioned about why 2 functions should not be rational, okay? So the intuition was that 2 functions should not be rational because in the general non-abelian case, because otherwise you would have too much regularity among the Frobenius operators at various primes, okay? So that was the intuition. But so what do we have here? So here, actually, we have a differential equation, right? So this L is a Picard-Fuchs operator. You have a differential equation, and forget what this is on the right-hand side, what this A's and psi's are, that doesn't matter. But what you have here is a rational function, okay? You agree with that statement? This is a rational function. And these b's and a's are also rational functions of psi and so on. Anyway, this is a rational function, and this Picard-Fuchs operator also is a differential operator with rational coefficients. So the statement is the two function might not be rational. Okay, that's too much regularity, but it could still be a solution of a differential equation with rational coefficients, and then it knows about the Frobenius mod p squared. Okay, so that's sort of you know, slightly weaker than having a rational one, much weaker probably than having a basis of two function which is rational in the general case, but still an interesting case. So what could happen is that the natural basis of two functions in the non-abelian case is actually a solution of a differential equation with rational coefficients, even though itself is not rational. Okay, but that's sort of speculations, and well, here are more speculations, which are sort of these you know, pressing questions about mirror symmetry that I mentioned during my talk, which I've put back together here. Actually, this is what I just mentioned here. So you can have, in fact, these two functions as solutions of differential equations with algebraic coefficients. We don't really know the interpretation, the enumerative interpretation, but I'm convinced it's there. I mean, it has to fit in, otherwise this entire duality from the physics point of view would break down. And this should be true. So this is the green statement should be true both for you know, the extended case, this relative case with algebraic cycles, and also the absolute case where you have these man points. And yeah, let me stop here. Thank you very much.
Okay, thank you, Johannes. Good. Any question in the recorded session of questions? Well, I have many. So in your last non-homogeneous differential equation, this is some families of Calabi-Yau varieties which is explicit, no, that you didn't write.
No, this is I sorry, I only flashed all these things, but there is a continuous story here. Not all equations are written in the slides. Okay, so this is the quintic, first of all.
This is the quintic with different rational curves.
It's the quintic with this curve. So
okay,
these equations define a curve in the quintic. So the x's are the you know.
So they are defined over some. Okay.
Let me say. Let me just go quickly over these equations. So the x's are the you know, projective coordinates on P4. Okay.
Mm-hmm.
And then you have a linear equation with a coefficient that's called a, and another one, and then you have a quadratic equation with coefficients called a and b, and so it's a conic.
I see.
And what you can verify is that this conic is contained in the quintic. So this is a conic in P4 to begin with, and the conic is contained in the quintic. I mean, in this Walk family of quintics, precisely if those two equations are satisfied. So 1 minus 2az plus 4ab squared z equal to 0, where z is the coordinate on the quintic family, right, on the Dwork family. I mean, some coordinate on the base of the family of quintics, and this other thing. So that's the global cycle. Okay, so a and b are algebraic functions of z in that case, right, just by the virtue of this equation. And then you can go further. You can and then you can calculate the inhomogeneity just, and it's this thing where psi is some simple function of z.
Do you know the Lagrangian in the A side of this? I mean,
no, I don't know.
Okay. But you accept that there is some Lagrangian, there is a mirror symmetry.
Mirror symmetry, there is a Lagrangian. It's not that I expect, I know there is.
Okay. Okay.
No, but what I'm, okay, I don't know if, yeah, you should ask the question. Otherwise I will.
Okay. Eunice, if you stop recording, then we go to the non-recorded.